Good morning to all. Myself Dr. K. Manoharan, Associate Professor, Department of Biomedical Engineering. So today class we are going to discuss about the subject biomedical transducer and sensors. So the unit will be fundamentals of measurement. So first topic, the signals and noises in the measurement. So what are the signals present in the device, how you are going to measure it, and what are the noises that affect the system. So here we are going to see about measurement, signals and noises, amplitude and power, power spectrum, signal to noise ratio, and different type of noise that will be affect the system. The first one is measurement. So measurement is a device that will be used to determine the quantity of characteristic the property, or we can say the state of an object. So what is the state of present object that will be measured by using this measurement? It determines the quantity characteristic the properties. The quantity being determined is called object quantity of measurements. Some quantities can be estimated by a human senses such as through visible observation. So from observation itself we can say that how much of quantity available. So some quantities only possible. Again, for objective, reproducible and quantitative results, the instrument should be used. So measuring instruments will be used to determine that particular quantities. So if we are measuring a voltage, we can use a voltmeter. Similarly, if you are like to measure a current, we can use an ammeter. So voltmeter, ammeter, wattmeter, we have so many instruments. Depending upon our application, we can use that particular instruments. Again, the measuring system provides the results as an output which depends on the type of instrument used. In electronic instruments are used, the output is in the form of electronic potential. So whatever the output we are going to measure in terms of voltage or in terms of current, we need to use this electronic instrument. So electronic instruments produce them in terms of electric potentials. The output can be converted into digital value if needed. So normally it will be in analog form. Sometimes we need to store it or we need to transmit that information. So for that it should be a digital form is needed. There we can convert from analog to digital conversions. In original or a physical or a chemical quantities, it is transformed to the convenient form such as electronic potential or a numerical value in the measuring instrument. Next will be signal and noises. In measurement, signal is a component containing information about the object quantity, while noise is a irrelevant component. That is, which is the relevant component which is required, that will be considered as a signal, and which is irrelevant or not required, then that will be considered as noises. So depending upon application, it will be varies. The signal is described component where noise is unwanted. Signal and noise are not defined by their physical nature but by their observer's intention. So we cannot define that this is the signal and this is noise. So it depends upon that which we are measuring, and the other things will be considered as noises. So whatever you are going to measure it, that will be considered as a signal. Whatever the irrelevant information, whatever they are not measuring, that will be an irrelevant and that will be considered as noises. So for example, we can see this EMG signal are useful for studying the muscle activities. So whenever you are studying this muscle activity, we need to use this EMG sensors where we use this EMG signals. So but the noises when it is studying then nerve action potential. So whenever you are studying a nerve action, there muscular activities is not required. So there the EMG signals will be considered as a noise. Same EMG signals whenever you are studying a muscle activity, there that will be considered as a signal. Whenever you are studying a nerve action potential, that same EMG signal will be considered as a noises. That's why it is defined by observer's intention, not by physical nature. In general, the measurement, the distinction between signal and noise is arbitrary. In communication technologies, signals are clearly defined by the sender's intent. Amplitude and power. The biomedical instruments, object quantities are typically time varying, and unwanted time varying components will be called as noises. So this is superimposed by the signal. Electronic instrument output on electric potential containing both signal and noises, both are time varying. So whenever you are using an instrument, it normally measures both noises and signals. Amplitude and power describes the range of variation in time varying signals. Sinusoidal variation is a fundamental, as any time varying signal can be expressed as a sum of sinusoidal signals. So by using this sum of sinusoidal signals, we can express any fundamental variations. The root mean square amplitude is useful for measuring a signal variability over a time period. So normally we use this RMS value for an measuring properties. Power spectrum. The power spectrum represents how the power of the time varying signal is distributed across the different frequencies. Power spectrum means power for different frequencies. So for each frequency, what are the power available? So that will be plotted, that will be called as a power spectrum. It is commonly used in signal processing, particularly in biomedical instruments like any EEG, ECG, EMG analysis. Power spectrum shown the signal power as a function of frequencies. It is obtained by computing the Fourier transform of the signal and squaring its magnitude. So converting from a time domain to frequency domain, we are using these Fourier transforms. It helps identifying the dominant frequencies and filter the noises and biomedical signals. See, which of the frequencies will be dominant, which are the not dominant. So that will be easily identified by the power spectrum. Also filtering noise, whichever the noise will be available in the spectrum, we can observe it and we can remove that particular noises. Signal to noise ratio, this is the most important. We can shortly say it is as a SNR. So it is commonly expressed as a ratio of signal power to noise power. So we expect noise power should be minimum and signal power should be high. Alternatively, we can take the peak to peak value of our RMS value of the amplitude and then noise also. In real time scenarios, SNR is evaluated in a specific frequency ranges. SNRs varies across frequency ranges due to the difference in the frequency spectrum and signal and noises. Higher SNR indicates the clear signal, whereas less indicates the interference will be, noise will be high. Thank you.